sparing time for us, for the participants from your busy schedule. You can test your slides, I think, before we start.
Okay, let me just. So is the slides visible?
Yeah, now it is visible. You can full screen mode. You can. Great. Yes. Try changing also. Sometimes it starts.
Okay, okay, visible, right?
Yes, yes, it's great. Yes.
Okay. Thank you.
Okay. So, is it a holiday for you today?
Yes. Today I think today is the 4th Saturday, I guess. So we have actually even Saturday is holiday.
Okay.
So anyway, holidays, we have something or the other.
Yes, right. How long you are there in ICT?
I joined ICT in 2015 March, so it's pretty long time. So for my PhD, I directly joined in ICT.
Okay, good.
So since then I'm here.
So I think a couple of minutes are left. We'll wait for the other participants to join, and we'll start sharp at 10:30.
Yes. Sure. I think it's actually very wonderful. I attended a few sessions.
Okay. Yes.
Which my classes are not clashing. I think
I think all the lectures were very nice and covering many aspects of modeling. So I think, young researchers and they will get benefited, I hope.
Yes, because I guess
and
it is I really look forward to meeting offline as well.
Yeah, sure. Actually, now there is no problem with the offline programs, but this FDP was planned quite some time back, when there was the plan was to go ahead online completely, and so we had limited fund also. So in future also, I think we'll try to make it a regular exercise once in a year or maybe like that, so that this goes continuous. This becomes a continuous process, and people get acquainted to one another, get ideas. I think
actually it is. With ISI, in fact, we had also arranged a couple of programs on statistical methods for mathematical biologists.
I see.
So that's actually that we made it kind of a regular program every year. So till lockdown, actually we consistently 5 years continuously have arranged it.
Okay.
But
great.
we are again planning to start it post lockdown.
Good. So maybe we'll also join.
Yeah. I think in Northeast there itself, I think Professor Bhattacharya arranged it a couple of times. In Nehu, I think once we went there for 3 days.
Okay.
It's wonderful.
So I think we can start. It's time now.
Yeah.
So, dear participants, good morning, all of you. And I have the privilege to introduce one of the distinguished speakers this morning. And I'm happy that today we'll see some hands-on actually, unlike other lectures. So it will be like more beneficial. People struggle with computational part of modeling.
Yes.
So I hope it will be beneficial for all of you, and some material for these sessions. So I shared in the, I think, our group, WhatsApp group, I think, and I'll share in the message also, I think, here. With these words, let me formally welcome our speaker. He is Dr. Omiranjan Bhumi. He is currently assistant professor in the Department of Mathematics in the Institute of Chemical Technology, Mumbai. He received his bachelor degree from Presidency College, Kolkata, with honors in mathematics and masters in applied statistics and informatics from IIT Mumbai. Prior to joining to Indian Statistical Institute, Kolkata, for pursuing PhD, he worked as a statistician in the Statistical Software Services Private Limited. He received his PhD degree from the University of Kolkata in applied mathematics in the year 2015. Dr. Bhumi has been actively carrying out research in the field of mathematical biology and applied statistics since the starting of his PhD program. His primary research interest includes the application of growth models in biology, biological research, species distribution modeling, etc. He has publications in leading international journals in the broad area of mathematical biology. He is also a regular reviewer of some leading international journals. Apart from the research work, he is actively involved in teaching mathematics at undergraduate level and statistics at postgraduate level. He is also actively involved in organizational activities, bringing the gap between biology and mathematics. PhD students are working under his supervision in the broad areas of applications of statistical methods in mathematical biology. With these words, I once again welcome Dr. Bhumi and request him to deliver his lecture. Dr. Bhumi, please go ahead. Floor is yours.
Thank you very much for the warm introduction. And it's truly a privilege to be a part of this program. And I would like to really thank you, Professor Jamal and Professor Chattopadhyay, for giving me this opportunity to interact here in the audience and discuss some of the things which are our interest, and mostly in the field of uncertainty quantification, use of statistical methods in the mathematical biology research. So let me share my screen. So as I think we have, as the topic says, that statistical detection of parameter variation in biological growth models. So let me share my full screen. Okay, this is the topic which is stated there. It goes like this. Just to ensure that, I shared two materials in the group, where in the first group we have some of the derivations and how those things are being implemented actually using R. So that complete code is now available to you. So you can execute those codes and run, and I'll explain over here, and we'll try to take some understanding also about the process, how actually we are building it. So before going into that, I think the starting of the program itself of this, I was in the inaugural program as well, that Professor Chattopadhyay has said that there is a huge applications of R in the field of ecological research, in particular ecology, epidemiology, and it's providing wonderful research structure with the with the theoretical research. So let us try to understand this 3 or 4 slides is just kind of a motivation that how this software R is becoming one of the leading tool in research in mathematical ecology, mathematical biology, or statistical ecology, this field. So now we all know that in the field of research, and particularly in several domains, actually, I think it is something called as reproducibility crisis. What does that mean? That many of the research papers, they are producing a lot of graphs, a lot of and a lot of research, a lot of outputs, a lot of data. But however, when these are being run again and in the same lab, they're not able to reproduce the same thing. So this is British Ecological Society. I think it is around 8 years back, around 2013 or 2012. They published a guide to reproducible code in ecology and evolution. So why this programming part is so much important in here? So they said that they publish in their website, they give this. It appeared in the Adventure with R by Sylvia Tipman in the Nature News. It's published in 29 December 2014. So see that this is the R software where one scientist is sitting over here, and it's the logo of R, which is horizontal making, and scientist is moving. But it is talking about that a rising tide of R. So increasing proportion of research articles that explicitly reference R or an R package. So if we look at this agriculture and biological sciences, this red line, we see that it's indeed an exponential growth. So starting from it is happened in 2014. So the graph is still 2014. So after that, in last 8 years, there had been a whole lot of development in this domain. It's kind of a super exponential growth happening in terms of packages and other things. So biological sciences, who really requires this domain, many researchers also say that 21st century is the science for biological sciences. And R is certainly taking a wonderful a leading role over here. So why actually R? So what they're saying that the way we do science is changing. Data are getting bigger. So it's no longer the time that when as an ecological data for applying our mathematical techniques, for applying or validation of the models that we are building, there had been a sparsity of data. But however, the situation is changing, and very rapidly it is changing. So this Natalie Cooper and Pen Yong from UK, they are saying that the way we do science is changing. So data are getting bigger, analysis are getting complex, and governments, funding agencies, and the scientific method itself demand more transparency and accountability in research. So one way to deal with these changes is to make our research more reproducible, especially our code. So in particular, at least the domain or in which I work, so I find that this is something which I need to ensure that these codes are 100% transparent and everybody across the globe, anybody can access those codes. So the one which I have shared with you, which is the same code that we have written explicitly. So there is no hiding things. So what we want to ensure that, or as a researcher, we should ensure that our codes are reproducible. Whatever the science that we have done, that can be reproduced by some other people also. So R is now getting, once upon a time, a lot of other domain researchers, they were not able to, their kind of a MATLAB or other many softwares were more popular because R used to lack a wonderful editor. But now R has come up with a very wonderful editor, R Studio. But now R Studio is soon going to be, there is a new editor is coming up, Quarto. And then it has a wonderful document generation using R Markdown. That some of the Markdown file I'll share with you after the second session is over. So there you can make presentations, you can create HTML web pages, you can make applications. So many things you can make. And you can actually, lot of statistical and mathematical concepts that we can actually simulate those. And this is very much helpful in teaching as well. So it has become a very, very common practice that to see people develop R packages and to integrate their novel development. So I think it's more than 17,000 packages are available right now in R. So there is, you see that there is a number of increases in the R packages that which are available in this domain, right? So writing new package is interesting, but often not regulated as well. So when we are using some software as a tool, we need to be ensure that we are using the right thing. So they have provided some analysis workflow also, so that when we are doing research or when we are targeting a problem, what probably we want to ensure. That if you see the codes that which had been shared within the WhatsApp or also in the chat box, they see that before every code there is some comment is written, and after that, this is something which we have been following for a very long time. So this is very important because we understand that whatever the research we are doing, we are analyzing large scale databases related to climate data, impact of conservation for species, and talking about distribution models for plants under climate changes. So we want to ensure that everything somebody else can also reproduce it. So that's why this has to be done. So we need to take care of the code very, very clearly. So this is a guideline that worked, he had follows. So this is just a motivation for that why we kind of use R a lot, because it's provide a wonderful structure. And in addition to that, this is a free software, and anybody, you can write code, you can get code, you can share code, anything without any problem, without any licensing issue, you can share it. So that is the main wonderful part of it. And let us now get back to our, so just getting into the main context. So how many of you have seen this R window? I'm not sure, but if you just, this is, if you open it, R Studio, this is the kind of window that you can see. So as you see that there, you can, this is a wonderful view actually. It's like a MATLAB view. So if you just open it, so you see that here you can write script, and then you can write your, so this is a very latest development in 1 month or 2 months of time, that quarter new kind of development they are doing. And the notebook, then markdown, you can make web applications. If time permits, I'll show you some of the web applications which we have made. Then you can write down C++ file, you can write down your Python codes also here, you can write down SQL script, stand file. Those who are doing Bayesian, they are very much, a lot of people use stand. Right, similarly, HTML documentation, very wonderful HTML files. You can write books using R. You can write write many markdown files using it can be in Word, it can be this and that, many ways. So just to understand you that it is the document that contains, in the same document you can have your codes as well, you can have your writing as well, and you can have your uh, what is called how much output you want to show, how much you do not want to show. So it is like in the same document, in the same programming page, you writing your program as well, and you are writing your description as well. So everything is going in parallel, and it supports LaTeX as well. So everything you can do it. So this is one of the material actually which I had written just to keep this in mind, that the audience that I'll be serving in this workshop is that they consider a lot of nonlinear models, right? Because mathematics, if we see the literature in mathematical biology, the research papers that been published, either you say mathematical biosciences, psychological modeling, or mathematical biology, JTV, TPP, these are papers. We see a lot of highly nonlinear models are there, right? So we always come up with some assumption that suppose that the species or tree system, they are moving in that fashion, so they may create a lot of differential equations, and then we perform the rest of the analysis, stability, equilibrium analysis, and everything we do, and based on that we give some kind of decision. However, it is very important to consider that whether that learning of that model is driven by the data or not. So that is the periphery, or that is the domain where we come into picture, and we interact with mathematical biology, and we try to understand the process, and we provide that what kind of decision we are giving from the real data, that whether it making any kind of sense or not. So whether to make this model so much complex that it is difficult to implement, so that part also needs to be taken care of. So this is also one of the file that how this randomness works into play, and how we can approximate actually randomness for real life. So for example, a species is growing. So how do we do it? So just let me just run it, and you see that there are different options. So HTML file or PDF or Word file also you can do. So let me suppose that I did this PDF. So it's rendering. There are a lot of wonderful YouTube videos. These videos are available. We also explicitly cover it in a workshop for specifically designed for statistical methods and our programming for mathematical biologists. So like 5 or 7 days we cover all these aspects. But here I'll just show you, give you a demonstration. So yeah, we have just executed it. So it's being executed. So when this is coming, so that means it's being executed. Okay, so how much percentage is done? There some simulation is there. Okay, that's why it is taking more time. Okay, actually there a big simulation is there. So maybe I'll just take this. I'll just show you that what is the output that you. Okay, I think let me just stop its rendering, and so this is the PDF output which you will actually be able to see, which I'll be sharing after today's discussion. So for example, this is one of the example where, so you see that a lot of simulation is there. So that's why it was taking some time. Yes. So as you see that we can write down this take files as well inside this window. So I think as Professor Chattopadhyay was in his first lecture, I think multiple times mathematical biologists don't know the logistic equation. It is almost impossible. So at least this equation everybody knows, that Rx into 1 minus x by k and x0 is equal to 0. I'll get into my slides. Just before that, we know this is the solution. And when we get the real data, it's something looks like this. Something looks like this, right? This is in the left hand side, you have this actual graph, what you get by solving the differential equation. But when you see the real data, it's kind of a deviated, right? So these are something, or much variation can also be there. These are simulated data, so less variation is there. So I can control that. Now, you know that this is the logistic graph. This is first the species grows at an increasing rate, then the rate is maximum, then after that rate decays and it converges to carrying capacity K. This is the basic dynamics for logistic, we already know. Now the question is, when you are giving such type of data, from there you have to approximate that what is the time period at which population had the maximum growth rate. So that means we are talking about identification of the point of inflection. When you have a wonderful equation, nicely done, you can do the calculus, and taking the double derivative, putting equal to 0, we can find out the point of inflection. However, the question comes when we are dealing with real data, how to do that? And even if you're able to do it, how much uncertainty associated with there? Means, if I'm looking at a species, say for example, collecting the data for 10 years of time, and if you fitted some model, and based on that you said there at the 4th year it is going to have the maximum growth rate. Are you really very sure that it is the 4th year itself? Not really, because it's always a come with some kind of a confidence interval. It seems that the data is indicating that between 3 to 5 years the species has the maximum growth rate. At that point of time they had the maximum growth rate capacity. So answering this type of question, it requires, means when you are or mathematical biology or mathematical equations interacting with real data, and whatever decision we are giving, that must come with an approximate confidence interval, or the uncertainty, how much uncertainty is there. That's precisely I'm going to address over here, that as a mathematician, when I give a big model, small model or big model, it is immaterial. But when I'm planning to apply it in the real data, so it must be every parameters, every model prediction must be come with some kind of an uncertainty bound. So how to detect those, and how possibly we can get with an optimal model? Should we make this model very complex or should we make this model simple? That also should be dictated by the data and associated statistical measure. So this is the process that what we are going to do. And recently we have also developed some of the methods, and I'll discuss about that. So I think the question is clear that what we are trying to address. If we are given real data and we have our mathematics, as a mathematician, we have all sorts of mathematics, differential equations, everything we have. Now we want to see that whether this differential equation is giving adequate description of the real data or not. And from that, we want to derive some of the statistics. That some of the research questions that the biologists are asking, whether we can answer those or not. So this material, once you get it, you will be able to easily understand that what actually I have written. I've tried my best to write down explicitly all the things. So we know everybody that point of inflection is this. So this we can estimate, but how to estimate the uncertainty associated with it. So, and this document will also tell you that how we can come up with finally a confidence interval. Where does it go? So you see that everything is mathematics only there. So we are doing this only. So how can I get it such type of confidence interval for the real data set? So our goal, the kind of in our group, what the research we are doing. So everything, all our mathematical equations and everything, they all are being driven by real data, and we would like to give solution to the real data sets. Okay, so this is what is the starting point of it. This document also will be available to you so that you can explore. So let me come back to my main topic. What is the name is given. So it talks about the statistical detection of parameter variation in mathematical models applied to real data. So agenda of this talk is that we want to revisit the theory of parameter variation in the context of growth curve models. So let's see what is the area, how much developed this area in the field of mathematical biology. So we want to investigate biological growth models with continuously varying parameters and build connections between existing growth models. Let's see whether building those connections that gives us advantage in analyzing real data sets or not. That's our final goal, right? If we have seen the 2 years of pandemic, so in fact more than 2 years, now there had been a whole lot of thousands of models, many things have come just to predict what is the pattern of the COVID. Right? What will be the expected number of new cases or cumulative number of cases? Many mathematical models have predicted that. And we want to develop a statistical methods that actually can detect whether a parameters varies in a growth model or not. So stochastic variation we will not talk over here. We'll talk about only continuous variation. And we also want to develop an appropriate way of selecting the best model that gives us the most important insight about the data, and we'll show some applications. So what is biological growth models? So they are usually presented a differential equation that describes evolution of population over time. So basically talks about the temporal evolution. Of course, we have a partial differential equations that talks about the movement of the space in a space. We can have a 1 dimension, a 2 dimension also, a multi-dimension also. Right? But typically when we discuss about the predictive system in a space, so it's basically 2-dimensional partial differential equations, and we look at those in a with appropriate boundary conditions and all, right? But here in our context, we'll be talking about only about temporal evolution. So such differential equations that describe the rate of change in the population size. For example, logistic dx dt is equal to rx1 minus x by k. It talks about that dx determines at what rate the population sizes changes with respect to time. These growth models are usually developed for modeling the growth of population under certain assumptions. This is very important. At least when we interact with the mathematicians, we find that it is our inherent tendency that we consider everything under assumption. That assume that the population is growing like this, like this, like this. But the basic question is that the really population is growing like this? So shouldn't that selection be data driven? Let's collect the data and see that what is the most possible appropriate description of the data. Take that model as our basic model. So this is some of the questions has always haunted me, and now we are trying to address some of those. And this is one of the way how we can do that. Assume that For example, assume that the per capita population growth rate is a linearly decreasing function of time. This gives rise to logistic equation. So classical equation, and I think Marquardt book itself, mathematical ecology, Marquardt book itself, derivation is there. The first example. What is meant by a parameter variation? This is the example taken from Marquardt only. So first chapter itself, this example contains. So if you have the exponential growth model dx dt is equal to rx, x0 is equal to x0. So you all know its solution turns out to be xt is equal to x0 to the rt. And as we take the limit, if r is bigger than 0, then it goes to infinity. It's an unbounded growth, Malthus law. Now, it says that R represents actually the intrinsic growth rate. So it is very, so if I take this, consider this per capita growth rate means 1 upon, if I just take this, so if I just take this x over here, the 1 upon this, so this becomes a constant R. So that means it is irrespective of the population size, 1 by x dx dt means per capita change in the population size is a constant. Definitely it's not a workable solution, right? So to come up with different idea. What is that? That it is very, so scientists thought that the intrinsic growth rate, that actually as population size increases or as interacting with the nature, their intrinsic growth rate eventually decreases. So they consider that it decreases as an exponential decay. So here if we just put r is equal to this quantity, its solution comes to be this. X is equal to x0 to the power minus r0. It's an exercise given in Marquardt book. And in this case, interestingly, that if we take x0 is equal xt is equal to limit, then x0 to the power minus r0 by alpha. So that means when we had a unbounded growth, by considering this continuous transformation in this parameter, we actually got a bounded growth. The population settles down at certain value. So what is the impact of parameter variation? For a growth equation, if one parameter changes continuously with specific functional, new growth equations can be obtained. It's like opening up a Pandora box. We don't have to recollect a lot of equations in this field. This field is already very much overburdened with a lot of equations. So if we just tune one parameter or change one parameter with a continuous variation in time, we can generate new equations. The new equations may have completely different properties than the properties of the original growth equation. We just observe that, right? So the exponential growth has no upper bound, whereas the Gompertz has the bounded. But maximum size depends on the initial size. So difference with logistic growth equation where carrying capacity is fixed. So understand that. Don't get confused with the logistic, because for logistic we have a constant carrying capacity, whereas irrespective of initial population size, it always converges to K. But for Gompertz, if you start with higher population size, carrying capacity will be higher. If you start with lower population size, carrying capacity will be lower, right? So now the question comes that we have discussed. So an important point here, that the per capita growth rate is equal to constant is equal to r. So just that 1 by x dx dt is equal to constant. And for Gompertz, that per capita growth rate is an exponentially decaying function, which is r0 to the power minus alpha t, right? So this we can write down that 1 by x dx dt is equal to d log x d log xt, right? This is something what we can see. This is a very important implication. D log xt by dt means if I take an approximation of the derivative, that means log of xt plus delta t minus log of xt, right? So it's a small difference in the logarithmic population size, right? Therefore, if we have real data x1, x2, xn, suppose that we have a real data x1, x2, xn, then if we calculate the log difference And if we observe that that is approximately same over time, we suspect that the underlying growth equation is exponential. So if we are given a real data, that's the key point what we have identified or what we have used actually in our further analysis, that if you get real data, you calculate the log differences. So basically log of x2 minus log of x1, and then log of x3 minus log of x2, then log of x4 minus log of x3, and we plot these quantities with respect to time. If these guys remain almost a constant, so that's given indication that data has been generated or that has come from an exponential model. If it decays, that means it's come from a Gompar's model. This is the key point over here. So let's try to see a short glimpse into this literature. Is it worth studying what we have considered? A simple example, connecting the exponential growth with Gompar's essentially give a clue that such connections may be abundant. So from exponential, we can go to Gompar's. Similarly, from logistic also we can go somewhere. From other equations also by varying parameter we can go somewhere. So along this line, the most ambitious study actually was carried out by Robert Banks. Growth and Diffusion Phenomena. This is the book published in 1994. So if you can see that book, you'll see that a lot of variations, transformation are given there. The first study as per the literature, what we have seen in 1957, which was done by Udita, who actually give an idea that parameters can vary with time. But he did not explore it mathematically further, or did not try to see in the case of real data. So post 1994, what we observed that there has not been much exploration into this time variation in parameters in the context of biological growth curve models. So what we have done. This is something what we have done. So this is our recent exploration. Okay, so you have to read it like this. Say for example, we are having an exponential model. So we know it is r into x. So this line is coming. So here I'm using transformation r is equal to r0 by 1 minus rt. Then we get the equation of hyperbolic growth. Here we are coming as, if I, from this equation, we get a linear growth. From this connection, if I use r as this form, power law form, we get a curve model, right? From the confined exponential, if I use this r is equal to r naught sum r by k, we get a logistic model, right? Then again from here, from logistic model, if we use k is equal to, where the k is varying, for t large, this gives an exponential model, right? Here there is at the top, there is something, I think I will just yes, in the top there is a theta logistic model because of that, right? Then here you can see that for different type of transformation we can go into different models. Let's note that there are two different colors we have used. As you see that this is the color called confined exponential model, logistic regression model, sorry, just logistic model, exponential model, and theta logistic model. These four equations are put in a different color, the blue color. We just need to keep this in mind. So till now, fine, that we have done an exploration that what are the additional possible connection can be made. So these are many connections. So we consider our base model as exponential, and then we use different variations in R, and we found out various different analytical solutions. Graphs are presented in the online, in the material that which is given to you. So corresponding graphs are there. If we are having a logistic based model and you consider various different transformation in R and some transformation of K, there are various new different equations you will be getting. The idea is very simple. That the parameters, we are just varying the parameters, and what are the new equations we are getting. This is the, when base model is theta logistic or generalized logistic, then we make different transformation in R, and we see that how, what is the final equations are coming up. And we see that some of the many existing equations also we are getting, right? And some of the new, where there is no references, these are new equations, right? So that means this table gives you some new growth equations as well. So here, for example, we got a many new equations. So all these equations which are basically new equations. So all these are new equations, right? So here the base model is confined exponential. Now, when we perform a parameter variation, it's not necessary that every time we are able to solve it explicitly, analytically. So there is there are class group of models also where we have considered different type of transformation, and these are the equations which we have got. Those are not can be solved analytically, right? So the question remains. Now the question comes. All these exercises that whatever we have done, table 1 to table 3 or table 5, mathematically interesting. As a mathematician, would like to see and immediately calculate it and get it done. But interestingly, if somebody, my collaborator gives me real data, he said that which model should I choose? I want to predict something about the future of the species. So you have given me 100 models. Which one should I take? That's the pertinent question. So as a mathematician, we need to answer that as well. Let us try to see that how we can possibly answer this. So the question comes that detecting parameter variation. So from a mathematician point of view, that I can change that transformation and I can get a new equation. But somebody is giving me real data and asking which parameters in this model are varying. I can make a big fit of the data. I can using softwares, I can give a wonderful fitting of the model to the data. Either less complex model or more complex model. So that fitting I can give. But the question is that is this some particular parameter, this is talking about some intrinsic behavior of the species. Because we work in the field in mathematical biology, every parameter comes with some kind of physical meaning to it. So whether this particular parameter is varying or not, let's try to address it. How can we detect that whether given the data, the parameter R is following this variation or this variation or this variation? That is something which we want to do. Let us now understand. So we have proposed in 2014, we have proposed one concept called ISR, interval specific rate parameter. So what we have done basically, we have written every growth equation in this format. This is the per capita growth rate into B times GT or B times GXT. We know that this is called as a non-autonomous form, this is called as an autonomous form, right? And we call this B as a overall parameter. So that means if data follows this particular growth law, this particular B will remain constant. Let us try to understand what we are saying. An illustrative example. Say in case of real data, we are planning to calibrate the logistic model. So know the logistic model, kxt is equal to k by 1 plus k by x naught minus 1 e to the power minus 30. Plus error I am putting just to ensure that there is a deviation in the data, because when you collect the real data, you don't see a solution of a differential equation. You say those are scattered values. So epsilon ensures that scattered values. So R and K, these are assumed to be fixed but unknown quantity. And these guys are usually estimated from the real data, either by maximum likelihood method or by method of nonlinear least square. Typically what we do, that if we have for data Ti xi, at time point T1, I got the measurement x1. At time point T2, I got the measurement x2. And at time points here, there, and we minimize this x value minus this functional form, and t is going to be replaced with ti and whole square, and we minimize it with respect to r and k. So it's a minimization problem in two variables, right? So if I minimize this quantity, I am going to get a single estimate of k and r. So that means which will act as a minimizer for this sum of square. So here, this complete data that x1, x2, xn, this complete data has been utilized to estimate these parameters r and k. So that means what? I utilize the full data, I get a single estimate of r and a single estimate of k. Remember it. There is only one R hat and only one K hat. And it has utilized inter data for the full interval. So here I have data, different type of data, right? That's it. What is interval estimate? Our idea was that we will estimate yes, I could hide it. Thanks. Right? So we have a logistic growth model, suppose that. So what the previous process we have done, we have the data, we use the full data and minimize this quantity and get the estimate of R and K. But what here we are doing, we are dividing this complete time interval into different windows. And each of the windows, whatever the data I'm going to have over here, I'm going to use this much of data to estimate this R and K. So if this is my jth interval, if this is my jth time interval, then in that case, on this interval, I'm going to get an estimate of R and I'm going to estimate of K. So let me call this as Rj and Kj. What is the statistical setup for this? How to do that? So we consider that there are how many parameters are there? There are two parameters. Suppose R and K I want. So we are going to utilize three time points. So we are going to consider, so this is my mean profile of the logistic growth, right? And corresponding means at 3 consecutive time points, mu j plus 1 and mu j plus 2. Details are given over here. Then in that small interval, that jth interval, based on this in time points, the values tj plus 1 and tj plus 2, this is the estimate of this Rj which we have got. Given the data, everything we can calculate in hand. Similarly, for Kt also, this is the expression for Kt which we have computed. So again, everything actually we can calculate by using our own hand, right? And the and the codes which are given to you, they are also explicit computation for it. The code is already written. We have written it and given it to you. Okay. So now note that the data that you are getting, it's a random, right? So the estimates, the estimate of the intrinsic growth rate based on these three data points, tj plus 1 and tj plus 2, it is a random quantity. Because from the same location, if we again collect the same data, these values are going to be different. So that means Rj delta t hat, it's a subject to random variation. So how to understand what is the distribution or how this much variation is there, right? So ISRPs are random variables. And there are theories which is called as a multivariate delta method, whose material I will already share with you. There we can show that even such a very nonlinear complex functions, this is ratios, then minus, then division, then logarithm of this. Even for such a complicated one, the corresponding distributions of RJT or the local or the interval estimators, these guys behave normal distribution, and this variance is given by this. So from this variance, actually, we can compute that what is the approximate population sizes in that time. So where this variance of expression is the partial derivative of this function phi evaluated at mu, which is given by this. So it's a normal distribution. Again, for the k also, this is the same thing can be done. Again, for k also, this is normally distribution. I think small mistake is that this should be xi. So here xi we have written, so it should be xi. So rest of the things are guaranteed. So this is the expression which is coming up. Now, when we come up with, so this is the rule when we deal with real data. So this is the part which we have to do. that whenever we are proposing that there is a, so that this sampling distribution of a highly nonlinear function collected from the data, and on the other side you have equations from mathematical biology, we have to ensure that whether the theory we are saying its sampling distribution follows that or not. So let's just do a small demonstration of this, how we do it. It's a little bit of hands-on. Yes, this is a little bit of hands-on. So everybody can see my screen. Let me just make it a little bit bigger. So that later you, when you execute those codes, you can execute them easily. Okay. So we are considering a simulation scenario that suppose that your population size K is 100 or maximum carrying capacity is 100. So how do we execute it? We select a line and run. It got executed. So suppose that these 4 lines I want at a time, run, 4 lines got executed. Okay. So my initial population size is 10 and our intrinsic growth rate is 0.3. And T is the, I'm plotting it from 0 to 19. So using this command, we can plot it. And H is the difference. Difference means it is the step size, right? And this is the logistic growth model. This is the mean profile or mean function for logistic, which is K by 1 plus K by X naught, right? And e to the power minus RT. And par MF rho, if we plot it, this is the plot it looks like. We know there is a logistic growth plot, right? If you just make it type is equal to L, this is the plot you will be getting for logistic. Now let us create a lot of data from this. Right? What I'm doing here, that I'm going to simulate data from this particular, whose mean population, mean profile is this. Okay, I'm going to generate data, say 1000-minute trajectories, and get an estimate of R and K using the formula what we have seen. This process is going to be replicated again 1000 times. So basically we are performing a simulation to verify that whether that such a nonlinear function, which is Rj delta T hat, it follows the same distribution or not. So this is interval specific estimate of R, estimator of K, then you do perform a simulation. So simulation going on. Yes, it is done. So then we generate the histogram for interval specific estimate of R. So this is the, if you see this picture, this is the interval. So R we have considered to be 0.3. Can you see that? This histogram is getting centered around 0.3. Here also the histogram is getting centered 0.3. Here also it is the same. Right? So at every time point, so this histogram is based on the estimate of R based on the time point T is equal to 1, T is equal to 2, T equal to 3. So for one replication, I got a single value. For 1000 replication, I get 1000 many values. And I draw a histogram of this 1000 many values. Right? At the same time, so this is going to be for T is equal to, so there are total time points are 20. So I'm going to get last time point is going to be, or last estimate will be based on the data value 18 point, 19 point, and 20 point. So there will be total 18 many histograms. So without any hesitation, we can see that this is a kind of a normal distribution, right? Now only verification is that the estimate that we have provided, this is the expression, this big expression we have got, whether it's variance is this or not, whether it's mean is this or not, that is what we need to ensure, right? So let us compute. This is the mean what we have obtained, what is called as a delta method that I did not talk here. And then we have computed the variance. As you see that variance, I have computed the gradient of phi. So we compared all the partial derivatives here, right? Then we got this delta where. So this is the variance of the delta. So that means the histogram should have a variance. First histogram should have a variance which is approximately 5.0297 to the power 0.4. E to the power minus 4 means 10 to the power minus 4. Let us see whether it is happening or not. So what I did, I centered all these histograms at 0. So centered R wells. Now we plot a histogram and draw a normal density curve with the same variance and same mean which you have got it from the delta method. See, this so wonderful matching it is, right? So this is precisely where real data, mathematical biology and the statistics comes in between, right? So whatever the mathematical theory that using the Taylor's approximation, we got the expression for variance for Rj hat and Kj hat. They are basically exactly matching. So similarly, this is the same thing. So this is actually the variance which you are getting from the data, from the histogram. So this histogram, if you get all these data, you can calculate a variance of this. Similarly for this. So this red line is the variance of the simulated values over here. And now let me put a variance, which is the theoretical variance, which we have calculated based on this. This is the quantity. So this is basically what is the theoretical variance, which contains all these big things. Right? So see, that is a wonderful match. Right? So that means the theory that you are talking about, that is exactly matching, right? Now you need to understand one thing, that we now have constructed a profile for the intrinsic growth rate at different time intervals. We know that for logistic growth equation, R is a constant. It is the intrinsic growth rate. So that means if the population really follows the logistic growth equation, this interval estimate of R or this Rj delta T, these guys should provide a linear profile, but they should be constant around some value across all time intervals. Let us see whether that is happening or not. Let us make a blocks plot. Can you see that the R is showing a distribution, but mean R is values, these guys are getting concentrated around the certain values, right? This is precisely give you an indication. This is precisely give you an indication that such graphs gives you an indication that whether the parameter R is varying or not. So if your actual model underlying growth is actually logistic for the population, and if you calculate the interval specific estimate of R, then across all time intervals, this should remain more or less constant. If you see some particular deviation from it, that will give an indication, okay, so this particular parameter R seems varying over time. Clear? So let's try to understand it. So this is the simulation which we have shown. Then let us just do the simulation for K as well. So the same thing we have done it for K also, that big formula for K. All these simulations, I'm executing those. So either you can execute using the run command, or you can also press Control Enter. That is just I did right now. So let us use the Control Enter. And these are the all estimates of K over here, right? So here also for K also we can see that these all are approximately normal distribution only, right? And same thing is happening over here. So how did we do the simulation? Which I shown it to you, a kind of a hands-on. If you're in the offline mode, probably it will be very much interacting. I can do a lot of experiment as well, but here unfortunately we cannot do that. So how did you do this? So we simulated the growth trajectories for n equal to 1000 individuals. We did 20 times. We use the multivariate normal distribution with logistic mean and variance covariance matrix has certain structure. You obtain the estimate of Rj at delta t, which acts as a single realization for the sampling distribution of Rj at delta t. We replicate this process 1000 times. So that will give us 1000 many estimate of distribution Rj delta t. Then we check the accuracy of delta method by plotting the approximate distribution by using delta method and simulated sampling distribution. This for Rj hat, estimated variance by, and this is the one by delta method. Red one is by estimated variance by simulation, and this gray one is the theoretical. Then we have visualized the simulated realizations by box plot. This is the plot which we have already shown it to. What is happening with K? K also is the same thing, as you see that. So for a logistic also, K is a constant, it does not vary. And you see that the approximately the mean of this K remains around this. So what is the observation? So what is the similar task what we have done for R that we can do for K as well? So then you conclude that the box plot of the distribution of ISRP and R and K, that there is no variation present in parameter. So in this particular context, R and K does not vary. A natural question arises, what will happen to these histograms if we consider logistic growth equation with varying parameters? Which in this case, our population is logistic, we simulated from there and computed the interval estimates of R and K. And we observe this guy does not vary. Now, suppose that we simulate data, perform this experiment from a logistic model where the parameter R varies. Let's see. So suppose that is logistic growth equation with varying R and K. Suppose that R is equal to R0 1 plus Ct. That means linearly R is varying. Look at that. It is the same formula for RJT. Can you observe that the histograms becoming? So earlier histogram was like this. And now when R is varying, oh sorry, this one is the when R does not vary. And when R is linearly varying, and we use the same formula and see that this linear profile is being shown by the R. This experiment is when R is varying with power law, where C actually is less than 1 that we have considered. So you see that this is the profile it is being shown. So it is a very powerful indication. There's that simple idea that if we simulate, if we find out the interval estimate, in different intervals we estimate the parameter. And if you plot them, if this guy, their pattern is going to tell us whether the underlying model is adequate or we have to consider some continuous transformation. And what would be the continuous transformation? That is also being dictated by this analysis. Let's see. So what is the connection to real data? So you have a base model. So you consider some base model. You get the data, draw a scatter plot, and based on that you start with the model. And then you consider some time varying functional form of the parameter, and that will get the final model. If biologist from the field knowledge, you know that the parameter varies in that fashion, it is well good, you take the final model. Or suppose that no prior information is available. The biologist came to you, tell that I'm using a 3-parameter model and I do not, it seems that some of the parameters are varying with time, but I'm not able to identify. So that means no prior information available, only data is there. So in that case, you start with some model, this basic model, base model. It could be exponential, it could be logistic, it could be theta logistic, it could be confined exponential. That 4 blue box we have shown. And you find from that, you find out the R and you consider different choices of R. So it can be different transformation of R. One transformation will give you model 1, another will give you model 2, some will give you model 3. Which would be the identification of the transformation? That can be chosen by the ISRP profile itself. Now note that here, it is very important here. If we did not know this method, what we have to do, and no information is available, I have to tell my computer that build this model 1, build this model 2, and build this model 3. Usually these models becoming heavily parameterized and becoming highly nonlinear. So there is an extra computation involved there. But now what I am asking that you get the real data. This is your time. You calculate this RJ delta T, right? And check its profile. How does it look like? Is it exponentially decaying? So if you have a linear, there are 2 parameters to be estimated. If it is an exponential decaying, there are 2 parameters to be estimated. If it is a constant, no question at all. So it reduces the computation heavily, right? So, and various different, if he is not happy with the 3 transformation, you may have 10 transformation. So 10 highly nonlinear models to be fitted, rather than you are fitting just on the ISRP profile, and that computation time would be very less, and you are fitting with simple models, with simple equations. Take me get back to the original, the table that I have shown you, so that you can connect with it. Yes. Now, in original scenario, you had to fit these equations, such highly nonlinear equations. But now, our proposal is that you fit these equations, which is less parameterized and simpler in nature. And from there, which equations fit the best? Suppose this is the best fit. So you choose this equation for your data. So this is a significant reduction in the computation. Right? So let us try to see some of the real data analysis, how actually we can analyze those real data. So for example, there are a few data points, data sets we have considered. Since it is a new proposal, it's not only probably good idea to apply only in the case of epidemiology. We have considered some other growth data also, from some cattle growth data, or some, in fact, market research on sales data as well. And we have also considered some cases where K is also varying, the parameter is also varying. This is an example taken from Banks itself. So COVID data. So what we did? We make it in such a way so that somebody else can also use it for their research problem. First, we plot the size profile of the data and see whether that it follows logistic model. Next, to know about the possible variation in the parameter, we plot the ISRP profile of R for the data. This is what we have done. So this is the ISRP profile that we have calculated, and these are the ISRP values, these gray values, which are based on the logistic one. Okay. What is the next? Then the ISRP plot clearly see that the variation in R is present, because RJT does not seem to be a constant one. It seems that there is a decreasing trend in RJT, right? So that means there is a decreasing trend in RJT. Now, instead of fitting the original data, we got this ISRP profile, and we are now plotting, we are now trying to find a suitable function which model the continuous variation in the value R. Now, what are there may be some possible candidates that models the decreasing pattern in R with this time. One is the linearly varying, linearly decreasing with time, which is not the case, but just for sake of completion, we have done it. Extended logistic, which is a decreasing one. Hyper exponentially varying R, so that means it is a e to the power minus alpha t, or hyperbolically varying R. So that means R by C by 1 plus alpha t. Right? The table contains that complete list. Now we feed these equations, okay, and try to see that which one is the best coming. Then we fit all varying functional form for R from our table, that the table that we have provided. Then we calculate the Akaike information criterion and RMAC. AIC means archaic information criteria. That's basically tells that how good the model fitting is. And this is also RMSE values, root mean square values, right? And selected the best fitted functional form, right? So the model with the minimum root mean square error. So the minimum distance which maintains, that we are going to select as a best model. To check our result, we also feed the new set of models for those varying R and also calculated AIC and RMSE. If you see the gray lines over, there's a gray boxes you can see. These are actually real data. So in the original data, we fit all different various models. Fit logistic, fit linearly growing, fit linearly decaying R, fit this fourth we have fitted only. We fitted some extra model also. Extended logistic, exponentially varying R, exponentially decaying R, and different models. Now out of them, which one is coming out to be best? The best variation which is given over here, that should also give the best fitting over here. This is what our claim is. Because here all this model, lot of complex functions needs to be estimated. Here, these are very simple. So if this best fit coming reflected over here as well, then we can conclude that logistic model with hyperbolically varying R is the best fitted model. So here hyperbolically varying R actually coming out to be the best fitted. Then logistic with varying R, this yellow line should come out to be the best fitted model. Let us see what our analysis says. So for all these models, so this is for the RJ profile. So different type of variation, we see that this is the minimum RMSE values, 0.13, mark at bold. And this is also the minimum AIC values, minus 1.135. So AIC value is the minimum that considered as the best model. Now note that linearly varying R and extended logistic, they does not have any significant difference in the AIC values. Not even this exponentially varying R. This is also not. And this is many of the research, at least in terms of COVID, when it comes, there has been a floods of research have come up, even within the just 4 or just within the 6 months of time. If the research gets saying that it is approximately more than 50,000 research papers has come up. So if you just search over it, every time it comes to be COVID only. And we thought that let us try to have a look at some of those papers. There are many research papers, they just fit a predictive model and give the decision. This is the best model. However, and many papers who has given decision based on the AIC values. One needs to understand that without a significant difference in the AIC's values, even suppose that one model is given AIC value minus 101 and this value is minus 108, they are actually equivalent, as if they does not have much discriminatory thing. So yeah, unless there is an AIC difference is greater than 20, it's a thumb rule. Unless there is a difference of AIC difference values which is more than 20, we cannot say that which is a better model than the others. So in this case, we can say that this hyperbolically varying R is performing the best, the first one. Then for each different types of model, we fitted also the final model. Then RMSE values calculate for all the model and see that for hyperbolically varying R, this is the least, this is the smallest model, this is the least RMSE. That means this goes most closest to the data. In terms of AIC values also, this provides the minimum AIC values across all, right? So if we want to make a prediction or short-term prediction based on the data for the COVID number of cases, we should consider a logistic growth model with hyperbolically varying parameter R. This is the conclusion that what we have made. Similar analysis we have also done for other cases, cattle growth data. So as you see, this is the data that you can see. This is the size profile. This is the time, and this is the data for cattle, right? Then we fitted, see that we fitted logistic model over here. See that the pink line. Then if put an extended Gompers model with C is equal to 2. Okay, this model looks like PGR means per capita growth rate means 1 upon x dx dt is equal to b e raised to minus at and t to the power c. And this is the model for c is equal to 2, and this is the model, and another one is the dotted line which is c is equal to 1. Again the question comes, as a mathematical biologist, these three equations almost equivalent. From mathematical point of view, these three all are very different because they all have very different expressions after solving. But when we are calibrating these models with data, there are rarely any difference. Now automatically the question comes, which would be the best? Again we do the same process here. First we plot the size profile for real data, and we see that sigmoidal shape growth curve would be an appropriate choice because it seems like a sigmoidal shape. So we start with that. Next we plot the ISRP profile of R, and it suggests that the logistic model is not an appropriate for describing the growth pattern, because had it been logistic, then this pattern would not be the thing. There, this pattern would have been a straight line, this type of variation. That would tell that we are whether we are logistic or not. Where is that? This one. Right? This had been the pattern, this would suggest, but here it is not the case. First R increases, then decreases. So that means the ISRP profile shows a kind of a power law profile. So what do we do? Then we plot ISRP, and it is clear that the variation in R is present. So it is not a logistic, rather than a model where its base is logistic, but its one parameter is varying, which is R. Then taking the exponential model as the base model, right? We fitted this for RT, right? For C is equal to 1, we got the best fit, right? So extended Gompers model with C is equal to 1, this would give us the with C is equal to 1, this would give us the basically give us the best fitting. Now you need to understand this uncertainty quantification part. Many of the research papers who mathematical biology with very highly nonlinear and heavily parameterized equations, when these are being used for prediction purposes, and most of the research papers actually lack this analysis, that how much confidence I am if it's a similar model with 3 or 4 different variations of that model can also be appropriate, because somebody asks with different assumptions and we get different values and we get a similar type of analysis only, similar type of outcome only. So which one should we consider? So that means something which is performing on an average better, right? So what we did here, this is called as a model comparison by bootstrapping. What it does, so what I did, so you see that there are several trajectories are there, right? And suppose there are 20 trajectories, we randomly selected what is called as a simple random sampling with replacement. Let me show it over here. Let me just show it to all of you. Suppose that there are x is equal to 1:20. And if we print our x, so that gives me 1 to 20. So suppose that is 1 to 20 indices for the different trajectories. If I write down sample x size is equal to 20, replace is equal to true. See that I got a permutation of these values 1 to 20, and some of them it appears again. For example, 13 has appeared twice, right? Here 13 has appeared twice, right? Similarly, if I do it sample once again, this again we get, right? Say I'm saying that ID again, so there is a different samples I'm getting, right? So this is called as a simple random sampling with replacement. So what I did, I perform a sample, this comment. So it becomes 11, 13, 8, 7, 6, 3, like this. So that means from the original data, these rows are being, or these trajectory, these identified trajectories being selected, and do this complete analysis. And I store the AIC value. I run this sample command once again. Now this some new trajectories or some trajectory couple of times or thrice they appear, and now I take these trajectories and do this process once again. So I get one more AIC value, right? So for C is equal to 1 model, I did the same exercise 1000 times. For C is equal to 2 value, I did this same exercise 1000 times. And for logistic also did the same exercise 1000 times. The code is given with you, don't worry. Right? So what is coming up over here? So we get a distribution of AIC. So as you observe that for different samples or different bootstrap samples, the logistic for AIC is much higher compared to others. So main competing models could be C is equal to 1 or C is equal to 2. Extended Gompard, C is equal to 1, C is equal to 2. Now as you observe that there is a much portion similarities there. But on an average, the C is equal to 1, its average lies over here, and C its average lies over here. So on an average, the what is called on an average, the performance of the extended Gompard C is equal to 1 is better than C is equal to 2. Most of the paper this analysis is actually lacking. It should be a part of this. When we have a replicated observation, replication is there, this must be there. Because we need to understand it, we have our fancy mathematical equations, which are very insightful, very useful, and a lot of real life applications and implication as well. But we parallelly need to ensure that whether our big equation is adequately at describing the original real data or not, or just by chance we have got a good fit. So this plot actually ensures that the choice of C1, C equal to on this model is not by chance. For many different type of data sets, different type of also permutation combination also data we do, this C is equal to 1 model seems to performing better as compared to others. So this is basically uncertainty quantification when we are dealing with multiple models. In next session, I'll be talking about more of a like 3-dimensional models, different models. We'll try to explain that. But this is part is that how we can compare different models, which model is performing on an average better as compared to others. Similarly, sales data, I think sales, same thing we have done over here. So ISRP profile is giving us the most important indicator, right? So it's not exponential, it's not logistic, it's actually the Gompard. So this one would be the prediction of the sales. So anyway, this is again the same process we have done over here. And this is another data where K is varying. So what we have done over here, another situation we have considered, we have given the data. Now variation in R is not having identified. So we try to identify whether K varies or not. You know, we plotted it. If we consider this as an outlier, then K actually varies as a linearly decreasing function. So it can be hyperbolically decreasing, it can be it can be linearly decreasing, it can be hyperbolically decreasing, or it can be exponentially decaying. So if we did all these with the K profile, so we fit KT is equal to this, KT is this, hyperbolic and exponential, right? And then we see the corresponding AIC values, and we see that the linear form is the best fitted form. The linear form is the best fitted. We consider this an outlier. And you see that so wonderful fitting. So this is a fitting all the growth models which mostly you see, these has an usually an asymptote. But this is the model where K is varying, it does not have an asymptote. And see that it's a wonderful fitting. Any growth model that you are able to imagine, this probably would not fit over here. But that is the beauty of that understanding, or why this detecting parameter variation is important is this. There are different types of phenomena. So we always study this bacterial growth, they are increasing, and give the classical example of logistic asymptotic, there is an asymptote. But real life, it does not happen in that way. In some cases, the species grows, and after that, there is something happens, it decays. And again, so if you want to model such a scenario, then identifying the variation in the parameter with a little effort could lead to the correct model actually. So we also check about the variation R using ISRP or logistic model as the base model. It is clear that there is no variation in R, and which is also verified by the claims in banks. So the method that what we have proposed over here, the way we identified, this is also supporting the existing research. So all the technical details, including all the derivations and whatever it is there. So a heavy load of 3 supporting information is there. Each supporting information probably in terms of size is more than the length of the paper. So if you want to get all the technical details of it, in this paper have all the technical details, including all the R codes for every picture, every bit of thing. As we said, that reproducibility in research. So we wanted to ensure that every bit of piece of code is there. And a wonderful thanks to Akhtar. Akhtar is the PhD, my first PhD student. So this is one of the work from his thesis. And Supriya, she is a wonderful master student who worked with me in some project in Bayesian aspect of the growth curves. And this is the just recent work. So why I thought of choosing it, because this gives us an indication that how with simple model we can get into a complex model. And these are important for mathematical biologists for whom making those equations, giving a real solution is important. And I think the government probably have, or the society probably understood for the first time. Still I entered PhD, financial mathematics seems to be very like lucrative. But mathematical biology is such a wonderful subject, but rarely we did not find, even if till our MS, we didn't even know that there is something called mathematical biology. But now I think this pandemic has given given an understanding that mathematical modelers or mathematicians has a extraordinarily wonderful role to play in government decisions, policy making, and everything. And there, the uncertainty, whenever we are talking about such things, the uncertainty with real data comes into the picture. So as a mathematician, you also have to ensure that when you're giving a decision, how much uncertainty is there, that variation we need to give, because based on that, the policy making would be done. So what is the main benefit over here? Reduction in the number of model fitting exercise is significant here. And interval specific estimates for 4 model is enough. So we did not actually, all these models, whatever we see, these are not, we did not calculate anything on this. We just take, these are the 4 base model. Calculate the ISRP only for these base 4 models, plot the ISRP with time and check that what kind of variation is there. And that will drive you that what will be the best model. We should go over here, or we should go over here, or we should go over here, right? So this is a huge computational benefit that we have got by this method. So conclusion is that by extending the idea of Banks 1994, we have identified that several existing growth models in the literature can be connected. It's important. It's a kind of unification. There is recently we have proposed a unification idea that using a single equation, it's a 5 parameterized equation, whole lot of different class of growth models we can actually unify. So there is a single functional form which contains 5 parameters and very complex in nature. So if we think of that calibrating real data with that unification purpose, then I have to fit a 5 parameterized model to it, which is much heavier task. But here, we just have to fit simple equations, calculate the ISRP profile and fit simple equations, and that's done. That will take you to the, in which complicated model that you want to go, it will take you there. So we have shown that such connections between growth equations that significantly reduce the efforts in choosing an optimal model. So this is an important because we see that many of the real life applications, there are many models offered by mathematicians. They're very highly complex. There is certain concept called principle of parsimony. It says that if my aim is to go for a prediction, it's best that we come up with a simple model that would give me as good, that will give me as good as prediction, right? If my problem is not of inference, I only want to know the prediction. That is the only data I'm having. I want to predict. That's it. Nothing else. So rather than a 6-dimensional equation, 1-dimensional equation will be fine. So this our method actually hits that as well. So we proposed a method to identify whether the parameter in the model varies with time, right? So it is just, but that identification leads to a very significant reduction. So this proposed idea can be verified. We have verified the epidemiological data like COVID, and the biology like the growth data of cattle, and also in marketing. Future plan. So when we develop something, automatically doing that through this 1.5 year of process of developing this and writing thousands of lines of pieces of code and verifying all these things, we understood that what is lacking. It is something like this. This is very interesting. That you see that we saw that if we talk about, let me come over there. Where is the expression for the R and K that, yes. Now you just see that this expression for Kj hat is so complicated, right? Using hand, you need to calculate everything. Rj hat, you need to calculate everything. So if some new growth model is coming, then you have to do all that exercises again in your own hand. Now we are proposing, like, it is just we have already written everything. We are just proposing an automatic computation of this. With that local information, we get that local information and we perform a localized kind of maximization by which that automatically, without doing this hand calculation, we would be able to get automatically those estimates will get automatically by using, if possible, if time permits, we'll probably provide a package also with it, so that somebody who has the real data who can automatically get those interval estimates for whichever parameter he wants for whichever model. So that will significantly reduce our human efforts to do this hand calculation. So this is our next just plan, where we consider, so we can take a first 3 time points and we construct the likelihood of that and maximize it and estimate the growth rates. Then in the second, this T1 is dropped. This one we consider and construct the likelihood. We have actually done with it already, and it's wonderful results we have got. And soon we are planning to communicate this. So, and these plots actually, it is going to give us, so at each of the intervals, we are additionally provided testing plan also, that you thought that it is actually equal to this. Whether it is not, whether it is yes or no, that must be statistically tested. So at each time interval itself, we are performing this testing that whether the underlying model is true or not. So the idea is that if I have 20 time points, 20 intervals, and I perform this testing with model 1, model 2. Model 1 has passed 16-minute intervals, model 2 has passed in 10-minute intervals. So my model 1 is going to be a better candidate as compared to model 2. That's another model selection technique. Till now, it's not in the literature yet. So some of the references. So these are some of the references which you can see that. In particularly, you can have a look at this Pal Vomic. This is appeared in JTB in 2018. That talks about like evolution of model specific growth rate and its genesis and performance over Fisher's growth rate. So there is the usual the PGR we do, RGR we do, that is basically due to Fisher. And we are able to show that in that research paper that the methods that using interval specific estimates, if we want to identify the optimal model, it identifies the optimal model with higher probability as compared to the Fisher's growth rate. So that's, I think, the main breakthrough in this domain we are able to make since our proposal in 2014, where we have proposed that what is the interval specific estimator. So this is the Journal of Biological Physics. First time we have proposed it, which talks about simultaneous identification of growth law and its rate parameter. So we'll be estimating the parameters also and parallelly perform the testing for the growths as well. So relative growth rate or the per capita growth rate, what we are thinking that followed by 1 by x dx dt. Once the model is identified, there will be modification on that. So that is precisely, and based on that modification, we can have an advantage over the underlying model. So these are some of the references. And this part is important. This slide I'm going to share with you. If you want to know, have an introduction to biological growth models. So this is the link where you can go. So let me just show that link. Somebody raised an hand. Okay, discard. So if you just go to this link, sorry, I just crossed the time. So if you follow this link here, you will get an detailed introduction of biological growth model and how these nonlinear models are being fitted using R, and how they are being solved using differential equations using R. So this complete description detail I put it over here for this lecture purpose. I did little bit of modifications. So how that bootstrapping has been done for AIC, this is also given over here. So complete code is also provided over here. And how this real data being analyzed, this is also given over here. Right? Some cautionary fact about AICs also are there. So which most of the researchers actually that misses that part when. So we need to be very careful about it. So this complete coding is over there. So if you see this web page, you'll be, this is a part of my personal web page. So you can easily get a complete idea how this nonlinear models, least squares methods, and solving the differential equation, how everything can be done using R. So all the bifurcations and everything, whatever you do in MATLAB or anything, everything we do actually using R. I think somebody raised an hand, and just before taking that question, I think it is mandatory. Okay, thank you very much. And I think I took 6 minutes extra. Extremely sorry. I think somebody raised hand. I can address them.
Good afternoon, sir.
Yes, please.
Just one second.
Okay, sir.
Okay, go ahead. Start it. Yes.
Good afternoon, sir.
Yes, sir. Please. Yeah, please.
Sir, actually, you are creating model by logistic and other parameter you are considering. Sir, anybody can create model, but by choosing some data sets is, I'm thinking that was the important. So how you are looking at a specific data like OB data or some other data? So according to, might be that going to get good value. So what type of things you are focusing specific when you are downloading any data, like COVID, whatever you show to us? So because same experiment, if somebody are doing, they are trying to making that our model is good, other model are not good. When I'm seeing this all type of things, only few things are changing. Like sometimes they are changing like some parameter or same model, but by choosing some different data sets also, they are getting some different value. So can you tell to us how I can get idea about when I will going to choose some specific data set or data related to going to create any model? So can you give some idea, sir?
Yes. Actually, I'm under the impression that I actually throughout this talk I give that idea only. Is that we have got a real data, right? So for example, if I think my screen is still shared, right?
Yes, sir. Yes, sir.
Yes. I think this what the question that you are asking, if I see this COVID data, where it goes, what the question you have asked, this is precisely the step-by-step process I had explained here. If you have got a real data, how you can choose which model turns out to be the best one. And in general, in many cases, in several cases, it would be a very difficult task to. And here, please understand that in this case, the contextually it is different. In a sense that if we are having two models, one parameter, somebody put little bit slight change in that parameter it makes, right? But here it is not a little bit change. We are talking about an evolution of the parameters itself over time. A huge literature is attributed to that, but the problem is that people did not know, or we do not know that whether a parameter is varying or not. If you have used MATLAB, R, or any software packages, whatever fitting exercises you see, you run it, you get a single estimate of the parameter value, right? Yes or no?
Yes, sir.
Yes. So that is what is the question, that throughout the time interval, you obtained a single estimate of that parameter. So how would you understand whether species physiology is actually governed by an equation where their intrinsic growth rate is varying or not? So it is targeting, it is actually asking, it is giving more important, like significant insights about the biological process or the underlying process that we are talking about. Here, we are not for overall, for all the time interval, we are not providing a single estimate. We are in separate intervals. We break down this whole interval to smaller intervals. And in each of the smaller intervals, we are approximating that parameter. If the model you thought that it is true, where the parameter is a fixed quantity, then even if I estimate in the small intervals and I draw that with respect to time, that would be a constant. However, if it is not a constant, in that case, we need to look for that. The model that you have considered is not the correct one. So it should give some more, like we should select a different model. So for example, if you see that, another example I show you, this is the equation. Without hesitation, anybody, if it logistic, would say that this is the best equation. It goes almost with all the data values. But is that the underlying process is really logistic or not? So sometimes when we plot a size, say for example, in analyzing the physical problems, when you see the growth, when you see the displacement with respect to time, we seem to find something. We can fit an equation. But when we plot their velocity, we find a very different profile. When we plot their acceleration, we find a very different profile. So that means what we have thought of only by doing this, the velocity profile or the acceleration profile may have a much difference than this. So this is the equation. So whether logistic equation is the better or not, that must be analyzed in comparison with a set of or a buckets of model. So we need to consider a bucket. We need to consider a set of competing models and analyze different characteristic of each of the model in the light of the data, and which characteristic that we are proposing, it turns out to be most apt with the given data, that would turn out to be best model. In fact, we have provided a cross verification also, right? That this is the process you don't do for the right now, this process you don't do, right? This process, because we are the people who are proposing it for the first time. This process you don't do. You do this process. And even this candidate does not come, right? Because we don't know yet.
Yes, sir.
So here what we are proposing, that you can get into the optimal model with much fitting of much simpler equation, and then extrapolating your simple equation knowledge to a complicated equation to get the best equation. And it is verified also. What the best we have got over here, the same best we have got over here.
Thank you, sir. Thank you, sir.
Yeah, sure, sure. Thanks for the question. It's very important. It's a good discussion. Yeah, thank you. Yes.
Yes, I think we exceeded time a little bit. So I must say, Dr. Romeo, it was truly excellent because what I knew that, to learn any computing tool, it must be by trial and error and, by self-effort. But you made it so simple and, explain the things, small things. I think participants must be more confident now to use this type of tools in their research. Thank you so much. Let us see if there are a couple of more questions in this regard. Rotha, do you see?
Yes. I think even chat box, is there any questions? Let me just take it out. Okay. Okay, so sir, to apply this, we need to know the analytical solution of the differential equation. It's a question from Palak Goel. Actually not. So actually not. In the second half actually of the talk, this is whatever we have done. We have done this complete thing in a actually what is called as in a frequentist framework, what statistician says. But we don't have to go that much far. So let me just answer your question in this context only. So what you do, so we have given you one more table where actually we do not have the analytical solution. So this is the table where we do not have the analytical solution, right? So in this case, say for example, we are plotting the profile for t versus xt, right? But here dxt dt, which is the difference in the data. So we are going to plot the profile for difference in the data. So basically velocity of the data with respect to time, and try to identify, and based on that we are going to identify the interval estimates of the parameters. So where we had the xi expression, where in the expression it comes as an xi, there in all the ISRP expression it will be xi plus 1 minus xi. So that will be the expression will come. Nothing else will change. But we hope that in next 3-4 months of time, if everything goes fine, you can get rid of this as well, because we are making a computational tool which will do this process automatically. If you just give the model and give the data, it will over time, it will provide you all the interval specific estimates. So hopefully we should be able to get it. Yes, it's very interesting question, And when we are developing this tool, this question actually came up. That's why that an additional table in the research paper actually got, where we do not have analytical solution. Very interesting question. So if it
Dr. Romeo, there is another, I think, from Palak again. It's regarding, is epsilon in logistic growth model is to address the noise in the data? If yes, then how to choose the value of epsilon?
Okay, so this logistic growth model is to address the noise in the data. If yes, then okay. So very frankly speaking, look, when this is only for the simulation purpose. When we deal with the real data, we actually do not have any control on that epsilon. So rather than, when given the data, we feed the equation and we then get an estimate of the error, and then square those error and take an average of that. So that actually gives an estimate of the variation associated with your epsilon. So that means how much the data has deviated from the original, from the true growth profile. The question here is very much pertinent for another reason. Here we have considered epsilon to be very small. The reason is, let me, so you have almost asked a question which is our just next research agenda, which I gave the future plan. So let me just show you over here. Thanks, it's a very wonderful question actually. So see that when we calculate the estimates by hand, there are a lot of exponentials, logarithm, diffusion, inverse, and other things, right? So what we found that epsilon, if we simulation, if we put this epsilon to be very high, these formulas become unstable. When we are dealing with the data where noise level is low, these guys perform very well. although these formulas are now being used and many researchers also have used it in the field of growth modeling. But our recent exploration says that these estimates, so if I consider, say, for example, using epsilon a bit large, I simulated 1,000 many simulated scenarios. What we observed that out of 1,000 replications, say 250 or for 300 replications, they fail. The reason being, for many of the simulated trajectories, this computation is not possible. Either it becomes logarithm of the negative value or something like this happening. So that is why these estimates are fine. For many real applications, these are already being applied, and we have also applied. I can cite some of the examples of research group from Italy and some research from India also. They have also applied this method. But now this is another drawback that we have found out. We have actually sorted it already, where we don't have to go by this hand calculation. Rather than using a computer, actually, we can do this process and make this analysis very healthy and easy. Thank you very much. That's a very wonderful question, actually. Okay. Thank you.
Dr. Vivek, we can stop